Hello guys, welcome to econometrics. We're going to be looking at the autoregressive distributed lag bounds testing approach using e-views. The ARDL bounds testing is a statistical technique that analyzes the short-run and long-run dynamic relationships of time series data that are both stationary and non-stationary. Now, the key features of the autoregressive distributed lag bounds testing approach is 1. The autoregressive component. The model includes lagged values of the dependent variable to capture its own past behavior. The second one is the distribution lag component. The model includes current and lagged values of the independent variables to capture their effect on the dependent variable. The third one is the bounds testing. The bounds testing approach is used to check for long-run cointegration relationships among variables. Now, the positive side, or the wonderful side of the ARDL is that it is flexible. Unlike traditional cointegration methods such as the Igograngia or Johansen, the ARDL can be applied regardless of whether the variables are stationary at level or stationary at first difference. If you can remember in the last video we did, variables, for you to do an Igograngia or Johansen cointegration test, variables needed to be stationary at first difference. So unlike that, the ARDL makes use of variables that are stationary both at level and at first difference. Now, what are the steps to ARDL bounds testing? The first step is to check stationarity using the augmented Gefuller, and we need to ensure that no variable is stationary at second difference. The second step is to select optimal lag length using the AKK information criterion. The third is to estimate the ARDL model. The fourth is to model diagnostics. To carry out model diagnostics, that is, carry out serial correlation test, homoscedasticity test, stability test, and normality test on the ARDL model. And the fifth step is we do a bounds test for cointegration. And then the sixth step is to estimate long-run and short-run coefficients, that is, if cointegration exists. Now we'll go into practical session. We'll go step by step. Please follow through. And the first step is to check stationarity using the ADF, and we need to ensure that no variable is stationary at I2. We can go to our e-views. Now we're working on GDP and government expenditure on social and community service. Now let us look at the stationarity status of GDP. Okay, we click on view, unit root test, standard unit root. We check ADF at level. Okay, GDP is not stationary at level. Okay, let's check for first difference. Yes, so GDP is stationary at first difference because probability value of 0.0175 is less than 0.05. Okay, we'll now check for social and community service. Okay, we click on view, the unit root, and then we'll check level at level. Let's see if it's stationary. Yes, social and community service, it was stationary at what? At first, at level. Stationary at level because probability value is less than 0.05. Okay, so we ascertained that the GDP is stationary at first difference and the government expenditure on social and community service is stationary at level. That is the first step, and no variable is stationary at second difference. Now we'll now go to the next step. The next step is to select lag length, the optimal lag length. Okay, we'll go to our e-views. Let us delete this, let us take away this. Okay, to select lag length we need to group. Okay, we need to go to quick, we estimate var. Okay, we put the endogenous variable is log GDP. Exogenous variable is constant and log government expenditure on social and community service. Okay, click on OK, and then we to find the optimal lag length we click on view, Then we go to lag structure, and then we go to lag length criteria. Okay, let me include 10 lags to include. Okay, yes, now this is the value, the lag test. You can see the AIC criterion is 4 lags, but you use 4 lags for this. Okay, let me save this file, but use 4 lags. We'll go to this thing, our PowerPoint. We discover that for step 2, the optimal lag length is 4. Why? Because the AIC information criteria has what? It's telling us that we should use 4 lags for our ARDL model. Okay, so then what's the next step? The next step we have to follow. The next step is to estimate the ARDL model using those lags. Now go to our e-views to estimate the model. We click on quick, we go to estimate equation. Okay, we go to estimation method, we click on ARDL. Okay, then we include our variables, log GDP. You don't have to include the constant term when specifying an ARDL model on e-views. Then we include log SCS and close the bracket. We leave the lag length at 4 since that's what we recommended, and we leave it automatic selection. Let the model give its own selection based on the four optimal lags. We click OK. Good. Now this is our ARDL model. This is our ARDL model. Good. This is our ARDL model. Look at variables. Watson is 2.04, which is a lot better. Yeah, our R score is 0.99. The significance of the model is less than 0.05, which is good. Okay, let's go look at a view of the model. And this is the model on PowerPoint. And now we cannot make interpretations for a model yet, because interpretations of ARDL will strictly apply if cointegration between GDP and SCS do not exist. So what we have to do is to test for cointegration using bounce test. To test for cointegration using bounce test, then we can now estimate long and short run relationship. But for now, all we have to do now is to check for model diagnosis. Check for model diagnosis to ensure that the model is okay. Okay, to check for model diagnosis, you've seen here that the Watson stats is 2.04, which shows that there is no serial correlation. But to further buttress on that, let us check the serial correlation LM test. The lags, we use 4 lags. We put 4 lags. We press OK. Can you see now? The Autoregressive test shows this. The Autoregressive test shows this for model diagnosis. That's what we're doing now. The Autoregressive test shows that there is no serial correlation. We look at the hypothesis. It says no serial correlation at up to 4 lags, and the probability value of the F statistics is greater than 0.05. So we accept the null hypothesis that there is no serial correlation at up to 4 lags for the ARDL model. Okay, let's also check for heteroscedasticity using the white test. Click on white. We click this and press OK. Good. Now the probability of F statistics is 0.8165, which is greater than 0.05. Now the null hypothesis says that there is no heteroscedasticity or there is homoscedasticity. So the fact that our p-value is greater than 0.05, then we accept the null that is homoscedasticity, meaning that there is no heteroscedasticity in the model. Okay, we now move to the next one, the normality test. Normality test shows that yes, that the probability value of the Jack-Barrier test is 0.964939. See, so this means that what the model is, variables in the model are normally distributed. Okay, we want to go further and check the stability diagnosis. You click on recursive estimate, click on Kusum test, press OK. Yes, you can see that the model is in between the upper and the lower line, hence our model is stable. Now that I've ascertained the model diagnostics, we discover that there is no heteroscedasticity, there is no serial correlation, the variables in the model are normally distributed, and the model is stable. The next thing we have to do is to do a bounce test for cointegration. We do a bounce test for cointegration. Now, how do we do that? A bounce test for cointegration. You will now click on View. We go to ARDL Diagnostics, and then we click on Bounce Test. We click on Bounce Test. Okay, and this is the bounce test. The F statistics is 5.703577, and 5% we have the variable that is stationary at level and at first difference. Now, at level and first difference are respectively the stationary and non-stationary bounds. Okay, let us look at this in an expanded version on PowerPoint. Okay, now look at the F statistics 5.703577. If the F statistics is greater than the upper bounds, which is 4.53, 4.523, 4.160, and also greater than the lower bounds like that at levels 3.957, 3.937, and 3.620, then means cointegration exists between GDP and expenditure on social and community service. That is the interpretation. The fact that F statistics 5.70 is greater than the levels and upper bound, lower bound, and upper bound at 5% shows that cointegration or long-run relationship exists between GDP and government expenditure on social and community service. Now, what is our next step? Our next step now, having known that cointegration exists between the two variables, our next step is to estimate long-run and short-run coefficients. Estimate long-run and short-run coefficients. Okay, we now go back to our e-views. We click on View. Then we go to ARDL Diagnostics. Then we look at the short-run. We click on Error Correction Results. Okay, this is good. Error Correction Results. Okay, now if you observe, we have the conditional error correction. This conditional error correction. And when we scroll down, we have the error correction. Now, what's the difference between these two? Now, the ARDL presents the conditional error correction and the error correction. And error correction is embedded and estimated in the ARDL regression model when evidence of existence of cointegration between variables has been found through the bounce test approach. While the conditional error correction regression is basically applied when there is a practical logical rationale to impose specific restriction on the model. Okay, so now for this study we'll use the error correction. I advise you the error correction model, and we'll look at the error correction model and see the Watson is still 2.04 initially, and look at the log, the short run government expenditure on social and community service possibly related to GDP and a significant at 5% level. Also the cointegrating times too. Let us look at an expansion of these results in the PowerPoint. Good. Now this is the error correction, and this is the error correction showing this. This is the error correcting term, which is negative and is significant at 5% level. And this is the government expenditure on social and community service, which is positive and significant at the 5% level. And this is adjusted R square. This is the significance of the model, which is significant at the 5% level of significance. And this is double Watson, which shows that there is no serial correlation as initially ascertained. And to find out, this is short run analysis. In the short run, government is spending on social and community services positively and significantly affected GDP. See, so for us to look at the long run relationship, we click on View, then we click on ARDL Diagnostics, we click on cointegration relation. Okay, this is the cointegration relation. This is it. So even in the long run, government expenditure on, okay, this is it here, the law on government expenditure on social and community service affects GDP positively and significantly. And now for the error correction term, this, the the same thing as here, is negative and significant at the 5% level of significance. The negative sign confirms that there is a long-run equilibrium relationship between GDP and government expenditure on social and community service. The coefficient shows that 2.58% of the deviation from the long-run equilibrium is corrected in each period. However, the slow adjustment signifies persistent shocks to the system. Now, this is a long-run result, the cointegration result we just did on the views. This is the expanded view. And what does it mean? In the long run, government spending on social and community services positively and significantly affected GDP. See? So that is it on the results on the short and the long run. Thank you very much. Please like and subscribe.